Hello students, welcome to Finite Element Method course. Today we will discuss stiffness matrix formulation of 16 degrees of freedom plate bending element, which is also called as Bogner, Fox and Schmit plate bending element, that is BFS element. Since second order derivative of deflection is involved in the degrees of freedom, this element is also called as C2 continuity element. In the last lecture, we had discussed 12 degree of freedom plate bending element, that is ACM plate bending element. Now this is 16 degree of freedom plate bending element, that is C2 continuity element. So the statement is derive the element stiffness matrix for rectangular plate bending element with 4 degrees of freedom per node, 4 DOF per node. So this is plate bending element, rectangular plate bending element we are considering for the derivation of stiffness matrix. So there are 4 nodes, node number 1, 2, 3 and 4. Now since degrees of freedom per node are 4 and total nodes are 4, so total degrees of freedom becomes 16. The origin of element is considered at node number 1. The size of element is A by B. So coordinates of node number 1 are 0, 0. Node number 2 are A, 0. Node number 3 A, B and node number 4 0, B. Now which 4 degrees of freedom per node are considered? Those 4 degrees of freedom are W, theta x, theta y and theta xy. That is, W means deflection, theta x is bending slope, that is dW by dx about y axis, dW by dy bending slope about x axis, and d square W by dx dy, this is twisting rotation. So this second order d square W, this second order term, due to this second order derivative of deflection, this element is called as C2 continuity element, right? So 4 degrees of freedom per node, total degrees of freedom are 16. Now very first step, as we discussed in previous lecture also for 12 degrees of freedom element, very first step is to write down the displacement function. Displacement function for the deflection W. Since there are 16 degrees of freedom, we have to select 16 elements from the Pascal triangle. So those 16 elements are, if you look at this Pascal triangle, this is Pascal triangle. Now 16 elements we have to pick up from this Pascal triangle, which are multiplied by generalized coordinates alpha 1, alpha 2 to alpha 16. That polynomial of deflection we have to write down. So which 16 elements you will select? So first is constant 1, then 2, 3, 4, 5, 6, 7, 8, 9 and 10. These first 10 are there. Now remaining 6 we have to pick up. If you remember the Pascal triangle lecture as well as the previous class of 12 degrees of freedom plate bending element, we had discussed. While picking up the element from the Pascal triangle, we have to take care 2 important points. First is always maintain the symmetry of triangle while selecting the terms, and second, always select the elements which are nearer to axis of symmetry. This vertical line represents the axis of symmetry. Always select element which is nearer to axis of symmetry. So 10 elements are up to this y cube are 10. Then we will select x cube y, x square y square, x y cube. This 3 become 13. Then we will select x cube y square, x square y cube. These 2 elements, because these are nearer to axis of symmetry. Instead of selecting these 2, x raised to 4y and x cube y raised to 4. Sorry, this is x, not x cube. This is x y raised to 4. x y raised to 4. Instead of selecting these two elements, why we are selecting these two? Because these two are nearer to axis of symmetry, right? So again, these 10 plus these 3, 13 plus these 2, 15, and last one is this central element because it is on the axis of symmetry, x cube y cube. So these total 16 elements we have to pick up to write down the polynomial of deflection for 16 DOF, 16 degrees of freedom plate bending element. I repeat again, these 10 multiply by alpha 1, alpha 2, generalized coordinate up to alpha 10 here. Then alpha 11, this x cube y, alpha 12, x square y square, alpha 13, x y cube, then alpha 14, x cube y square, then alpha 15, x square y cube, and alpha 16, x cube y cube. So like this we have to write down the polynomial of deflection. If you look at this equation, it is written like this: alpha 1 plus alpha 2x plus alpha 3y up to last element is alpha 16 x cube y cube. Now if we know the polynomial of deflection, we can find out the rotations very easily. Theta x, theta y and theta xy. There are three rotations here. Theta x is equal to dw by dy, that is deflection derivative of w with respect to y. Theta y is equal to dw by dx, derivative of w with respect to x, and theta xy is equal to d square w by dx dy. So we have to differentiate deflection with respect to x and y, and then xy. We'll get these three rotations, slopes. So now how to differentiate we know. First, if you take derivative of w with respect to y, that is to find out the theta x. So differentiate with respect to y this polynomial. We know that when you differentiate with respect to y, variable x is treated as a constant because it is partial derivative. So derivative of alpha 1 is 0, derivative of alpha 2x is 0, derivative of alpha 3y is alpha 3, first term here. Then derivative of this term is 0, derivative of this term is 0 because only x cube term is there, it is constant. Then from remaining terms we have to take the derivative with respect to y, we will get this expression of theta x. Similarly, if you differentiate the expression of w with respect to y, x, you will get theta y. If you differentiate with respect to x, when you are differentiating with respect to x, y variable is treated as a constant. So derivative of alpha 1 becomes 0, this derivative will be 0, y square derivative will be 0, then y cube derivative will be 0. These four terms derivative will be 0 because y variable is treated as a constant, and from the remaining terms we have to differentiate with respect to x, we will get this expression. Now to find out the theta xy, that is d square w by dx dy, either you can differentiate this expression with respect to x because already we have differentiated with respect to y. So you can differentiate this with respect to x like this, or this expression we have which is already derivative with respect to x, we can differentiate this with respect to y. We will get the same expression from both. So if you differentiate one of the equation out of these two, again with respect to this, either with respect to x or this is with respect to y, we will get the expression of theta xy, right? So these are the four expressions for 4 degrees of freedom at each node of the plate bending element, that is BFS plate bending element, w, theta x, theta y and theta xy. If you write down these 4 equations in matrix form, you will get this. Such type of matrix you will get: w, theta x, theta y and theta xy, 4 unknowns, then 16 columns because there are 16 terms, and alpha 1 to alpha 16 generalized coordinates. So this matrix is called as delta matrix, and this matrix is called as parametric matrix, and this is alpha vector. So this matrix is called as parametric matrix. Already we discussed in the previous class of 12 degrees of freedom plate bending element, parametric matrix. Okay. Now next step is, once you find out the parametric matrix, then we have to find out the connectivity matrix, which is obtained by substituting the coordinates of each node in this matrix. Here, instead of this x and y, if you put the coordinates of nodes, what are the coordinates of nodes? Coordinate of node number 1 is 0, 0. Coordinate of node number 2 is a0. Coordinate of node number 3 is ab, and coordinate of coordinate of node number 4 is 0b. If you put these coordinates in parametric matrix, there are 4 rows for one node, and because of 4 nodes it becomes 16 rows. So this is node number 1. Node number 1 coordinates are 0, 0, x0, y0. If you put in the expression here, if you put that x equal to 0 and y equal to 0 in all 4 rows, you will get these 4 rows from the node number 1. Then node number 2 coordinates are a0, so x equal to a and y equal to 0. Then remaining 4 rows you will get. Then node number 3 coordinates are ab, x equal to a and y equal to b. Remaining 4 rows you will get for node number 3. And then 0b, coordinates of node number 4, that is x equal to 0 and y equal to b. You will get remaining 4 rows of the node number 4. So total rows here become 16, total column becomes 16. So this is 16 by 16 matrix, which is called as connectivity matrix and represented as C. So this is C matrix, connectivity matrix, right? This matrix is called as alpha matrix, this is C matrix, and this is vector of nodal displacement, that is XC matrix. So this is XC, this is C, and this is alpha. So same equation is written in the next step. X is equal to C into alpha. If you take C on left hand side here, alpha equal to C inverse into XC, right? Now if you put this alpha equal to C inverse into XC here, so you will get delta equal to P into C inverse into XC, right? So this one, this instead of this is delta, actually delta equal to P into C inverse into XC. So P into C inverse is called as shape function, that is n. This is called as shape function. How many shape functions will present here? There will be 16 shape functions because of 16 degrees of freedom, right? So P into C inverse, P matrix is 4 by 16 and C inverse will be 16 by 16. So finally you will get the answer of 16 shape functions from this calculation. Now once you find out the shape functions, then you have to write down the strain displacement matrix. Strain displacement matrix. So we have to find out the strains from the displacement. So for bending element, stress strain relations, strain displacement relation, strain is equal to, there are 3 strains, epsilon x, epsilon y and gamma xy. So epsilon x is equal to, in bending element, minus d square w by dx square, epsilon y equal to minus d square w by dy square, and gamma xy is equal to minus 2 d square w by dx dy. D square w by dx square, this is also called as curvature, bending curvature relation. That's why this is also called as strain curvature relation, right? Now we have to find out second order derivative of w with respect to x. Already we have determined the first order derivative. If you remember, this is first order derivative, dw by dx. If you differentiate this again with respect to x, you will get second order derivative, right? And then if you put a minus sign, you will get that expression. Similarly, if you differentiate this with respect to y again, you will get second order derivative of y, d square w by dy square. Okay. and here you already have d square w by dx dy, only you have to multiply by twice to write down the third strain, that is gamma xy. D square w by dx to dy, only you have to multiply by minus 2, right? So these are the strain terms. So we have to differentiate this expression, these three expressions. So there is no need to differentiate third one, because already there is d square w by dx dy, only we have to multiply by minus 2. Only these two we have to differentiate. This is with respect to x and this is with respect to y. If you perform that derivative, you will get these expressions. This is minus d square w by dx square, this is minus d square w by dy square, and this is minus 2 d square w by dx dy. So these are the expressions for strain epsilon x, epsilon y and gamma xy. Once you find out the strains, then you have to find out the stresses, which you can find out by using the stress strain relationship from the theory of elasticity. Stress is equal to d into strain, where stress, this is a stress vector, this is strain vector, and d stands for elasticity matrix. D stands for elasticity matrix. Now if you put the value of strain from this is strain, we have determined these three expressions. If you write down in matrix form, this is called as coefficient matrix, will be called as qxy, q matrix multiplied by alpha. For example, these expressions if you write down in matrix form, so here there will be alpha 1 to alpha 16 generalized coordinates, that is alpha matrix, and whatever coefficient matrix you will get here, this is called as B matrix, strain displacement matrix. Okay, this one qxy, if you put the value of alpha, that is C inverse into xc, this is called as B matrix, strain displacement matrix. Okay, so this, what is strain expression becomes finally, strain is equal to B into xc, strain is equal to B into xc. So same value of strain if you put here, B into xc, so stress become D into B into xc, stress becomes D into B into xc, that is the value of stress. So if you determine strain and stresses, the last step of derivation of stiffness matrix is to apply principle of virtual work to find out or to derive the stiffness matrix. It is similar to previous element, that is 12 degree of freedom. This is external work done and this is internal work done. The principle of virtual work state that external work done is equal to internal work done. Q is a external load vector, x is equal to nodal displacement because of external load. So load into displacement is called as work done. So this is external work done. Internal work done is equal to internal force into internal displacement. So internal force is stress and internal displacements are strain. So stress into strain is called as internal work done. Since the whole element, whole body undergoes the stress and strain deformation, we have to integrate that over the volume. So this is integration over the volume, you can say, or since it is a rectangular plate bending element, you can say this is integration 0 to A and integration 0 to B. It is a double integration. Okay, this will be double integration 0 to A and 0 to B. If you put the value of stress from previous step, this is D into B into xc, this is stress, and then if you put the value of strain, again B into xc, then D into B transpose over the integration 0 to A and 0 to B. This term is called as stiffness matrix K. This into this, right? And this transpose term will get cancelled here, and remaining is this xc term. So Q equal to K into xc, this is final equation. So using this double integration 0 to A and 0 to B, the vector matrix D into B into B transpose. Using this we can find out stiffness matrix of plate bending element. Okay. So this is derivation of stiffness matrix of 16 degrees of freedom plate bending element, which is also called as BFS element, which is also called as C2 continuity element because of second order derivative of deflection present in the unknown variables at the nodes. I hope all of you understand the derivation of stiffness matrix. In the next class, we will solve the next topic on the finite element method. Thank you very much.